Hello students, this is Dr. Sansom here to do the Prelab lecture for experiment 3, which is our single replacement stoichiometry reaction. And today in lab you're going to be focusing on one reaction but exploring it in a variety of different ways. And one of the things that you'll do is write out balanced chemical equations, ionic equations, and net ionic equations. So thinking about how those representations communicate what's happening in the chemical reaction. You'll also be creating diagrams at the molecular level showing the reactants and the products and how the atoms are rearranged into different molecules between the reactants and the products. You'll make some arguments supporting your claim of what you think the products are using evidence from what you observe during the reaction and reasoning about the types of reactions that you're dealing with. And you'll calculate how much product should come from a certain amount of reactants, or the theoretical yield. And in the experiment, you'll also calculate the percent yield, which is how much you actually got of your product compared to how much you should have gotten. Today, the process skill that you'll be using is information processing, and this is because you're going to be translating between things that you observe in your beaker and the symbolic language that we're using in the chemical equations, and then the drawings that we use at the molecular level. So you have to sort of transform information from one form into another. There are several reaction types that you should be aware of, and we'll talk a little bit more about this when we do the next experiment with all the different reaction types. But essentially, synthesis, decomposition, combustion, single replacement, and double replacement are all types of reactions that you can do in general chemistry or inorganic chemistry. And today we're going to be talking about single replacement reactions. In a single replacement reaction, you have one compound and you have one element. And in our case, this is going to be our copper 2 sulfate, that's our compound, and then aluminum is our element. So on the other side, we're going to get aluminum sulfate and copper. So when you're writing chemical equations, the ones that you're used to seeing are what we call the balanced chemical equation, or the complete equation, or the molecular equation. And this includes all of the substances written with standard chemical formulas. We're going to talk today about an ionic equation, or a complete ionic equation, and this includes everything, but it depicts them in the symbols the way they actually appear in solution. For example, if you have an ionic compound or a strong acid or a strong base, we know when it's in solution it's going to ionize and dissociate. So it actually breaks up into separate pieces, and we can represent that in the way that we write the balanced ionic equation. In the net ionic equation, it's just like the ionic equation, but we eliminate the spectator ions, which are not involved in the chemistry. Let's do an example here. If we're mixing iron 3 hydroxide, FeOH3, this is a red solid, and we're mixing it with 6 molar hydrochloric acid, which is a colorless solution. If we write out our balanced chemical equation, we are forming here a complex ion, FeCl4-, so that's why it's in brackets here, because it's a complex ion. And we can write out the whole balanced equation. We know that the hydroxides react with the H+ ions to make water. And because our FeCl4 has a negative charge, it needs one hydrogen to be the counter ion to balance out that negative charge. So that's our overall chemical equation, very similar to what you've seen for other chemical reactions that you've written. We can also write the balanced ionic equation. So notice what's happening here. This is a solid and it stays a solid. But when we look at something that's aqueous, we have to decide if it's going to dissolve and not dissociate, or dissolve and dissociate. And the way we decide is if it's a strong electrolyte. And hydrochloric acid does happen to be a strong electrolyte. So notice I'm writing it separately here, 4 H+ and 4 Cl-. Also over here, this compound, really we have the complex ion that stays together in one piece, but the proton is going to be separate from it. And then water, which is a liquid, of course, stays together. It doesn't dissociate. Finally, if we want to write a balanced net ionic equation, we're going to eliminate any spectator ions. In this case, that's pretty easy. It's just one of the protons that's the same on both sides. So we eliminate that and we simplify it to just the chemistry that's happening in our reaction. And if we were observing this reaction, it turns out this FeCl4- ion has a bright yellow color, so we would have our red precipitate at the beginning that was our FeOH3, and then it would dissolve and we would create this yellow solution that has the complex ion in it. So one of the things that you're going to be asked to do on this lab is draw molecular level representations of what's going on with the chemical reaction. And to do that, this is an example of what that might look like. Essentially, we want you to draw each of the atoms that exist. And for example, here, this is carbonate. If it's CO3, they're connected together, so we should see them connected together. And we should be able to distinguish between something like chloride and sodium, because they're different colors, and maybe you'll use a different system that's not color, but color is one way that you can do that. And what we've pictured here is called the complete ionic equation. So this is that sort of second level of the three levels that we talked about, where we've drawn things dissociated. This is our sodium carbonate, and the sodium ions are separate from the carbonate. And this is our zinc chloride, and the zinc is separate from the chloride ions. And then in the product, we're making this zinc carbonate precipitate. And in fact, the sodium and chloride ions are still just floating around, and they are spectator ions. So if we were drawing the net ionic equation, none of these purple and green dots would be here. This is depicting the complete ionic equation, and that's what we want you to depict on your lab report. Your lab report is also going to ask you to provide support for the claims that you're making, such as the type of the reaction and the chemical equation, by providing specific observations or evidence. Usually each substance has some kind of observation associated with it. And then you should connect the evidence and the claim with reasoning, which is how you decided on the type of the reaction and the products of the reaction. And this should include a reference to a chemical principle or a pattern. For example, if you know it's a single replacement reaction, then you expect that some of those ions are going to switch places and you'll end up with a different element at the end than you started with, and a different compound at the end than the one that you started with. One of the calculations you'll be asked to do is the percent yield. And this is a stoichiometric calculation, which you guys have done before. Essentially, to find the theoretical yield, you take your reactants and you use stoichiometry to get how much of the product you should produce in the reaction if all of the reactant is used up. And that's why we call it the theoretical yield, because sometimes experiments don't work perfectly. And so you get what's called an actual yield, which is how much you actually make in the experiment. And of course, the ratio of your actual yield to your theoretical yield can give you the percent yield, which you'll calculate for your experiment today. If in a problem you're given multiple different quantities of reactants, then you should always assume that you need to calculate the limiting reactant. Now I'm going to tell you about the exam, but first I'm going to tell you about safety. So for this experiment, the copper 2 sulfate solution is an irritant and harmful if swallowed, so you should be careful with that. And also you should perform the reaction either outside or next to an open window. It's going to produce fumes and it will be dramatic. So you need to really do it outside if you can, or next to an open window would be okay. Now for a couple of points about the exam. The exam will be done using Proctorio. There is a Proctorio test run under exam, so you can see what it will look like and how it will behave when you're taking the real exam. I highly encourage you to do that. You get a little bit of extra credit for doing it, and I think it will help ease your mind, make you feel less anxious about taking the exam with Proctorio. There are 20 multiple choice questions, and they cover experiments 1 through 4, which for us are the spectrometry experiment, the nuclear chemistry experiment, the enzyme catalysis experiment, including the simulation that we did, and then also this stoichiometry single replacement experiment that we're doing today. Most students take less than an hour, but there is a 2-hour time limit, so you should have plenty of time to prepare. I highly recommend that you go to review sessions and check the announcements on Learning Suite for when those are going to be held. Those will help you a lot in just feeling more confident and ready for the exam. And then in terms of the content that's on the exam, it's drawn from your lab reports, your pre-lab assignments, and the lectures that we have in class. And so definitely reviewing those, making sure you can do the calculations, making sure you can explain any of the concepts. Those would all be important steps to take. Okay, that's it for our pre-lab lecture today. Have fun in lab and good luck with your exam.